Hey, so we've been working on our probability distributions, and I would like you to imagine a little game. And this game is something you might have seen before, but basically, there's a series of pegs. Oops, let's turn on the marker. So you got a series of pegs in a shape that looks kind of like this, where they're all evenly interspersed. And what you do is you drop a little coin on the top slot. So you drop a coin right here. And basically it bounces its way down through the pegs. And on the first one, the way I built this board is that it's gonna go right here. But then there's a 50-50 chance that it goes left or that it goes right from there. So it could go this way or it could go this way. And then again, there's another peg right down here. So there's a 50-50 chance that it goes here or here, 50-50 chance that it goes here or here. If we draw another row below this, we can repeat this pattern here. 50-50 that it goes left or right, left or right, left or right, like that. So what I want to try to do is describe the probability that it's going to land in any of those end sections. And this is an example of what we're going to be studying called a binomial distribution. Some people call this a Galton board or a quincunx or a bean machine. And it's pretty simple. You just are basically using this to take a random sample of a process, and it could model like coin flips because maybe left is heads and right is tails, or it could model other things where there's evenly dispersed distributions. So let's start writing some numbers here. There is only, I'll use purple. There's only one way you can get right here. Then there is only one way you can get here and one way you can get there. There is only one way you can get here. It has to go left and left. But there are two ways you can get there in the middle because you could have gone left then right or right then left. And there's only one way you can get here. It had to be right, right. Or if we were doing flipping a coin, it had to be tails, tails, for example. Same thing down here. One way you can get here. Think about how many ways can you get to this location right here? Well, you could go left, left, right, left, right, left, or right, left, left. There's actually three total routes that you can get there. And by symmetry, this is also three, and this is also one. By this point, hopefully, this is looking familiar. If I add the next row of pegs onto my quincunx, which is such a weird word, I can, so hopefully you can predict the outcomes here. We can get here one way, we can get here four ways. The one route here and the three routes here make four routes right there. There are six ways to get here. Travel these three routes and go here, or travel these three routes and go there. Three plus one, and one route to get down to the corner. Turns out that this very simple machine that you can build is almost exactly the same as our good old friend Pascal's triangle. But I told you that these were talking about probabilities, and we know probabilities can't be bigger than one. So there's no way that the probability, for example, of this one right here, this cannot be six. That's not a probability. So what we go through is what we do is we go through the different total number of roots on each of those. And so the total number of roots is going to be the sum of the outcomes in that row. So the total number of outcomes here is 1, 5, 11, 15, 16. The total number of outcomes here, 1 plus 3 is 4, plus 3 is 7, plus 1 is 8. Perhaps you're seeing a pattern. 1 plus 2 plus 1, 1 plus 1, and 1 by itself. So what I know is that I can take the number of paths that get to a particular spot and divide it by the total number of paths. So the probability here, and I'm going to maybe switch colors to write the probabilities. So the probability here is 1 out of 1. Each of the probabilities here is 1 out of 2. Probabilities here are 1 out of 4, 2 out of 4, and 1 out of 4. Here we have 1 out of 8, 3 out of 8, 3 out of 8, and 1 out of 8. Here again we have 1 out of 16, 4 out of 16, 6 out of 16, 4 out of 16, and 1 out of 16. Okay. Now there's another way because, and before I say the other thing, this, like I was saying, could represent heads or tails. This could represent anything that has two equal probabilities. But there's actually another use for this sort of board as well. You may recall that the numbers in the uh, Pascal's triangle are related to our combination coefficients. So what I'm saying is n choose k, which the formula, remember, n factorial over n minus k factorial times k factorial. This is going to be this will give you one of the entries in the Pascal's triangle. So let's do a quick example. Let's say I did 3 choose 2, and I'd get 3 factorial over 3 minus 2 factorial, 2 factorial. That ends up being the number 3. That is the this is the coefficient of the table that corresponds to 3 choose 2. This one corresponds to 3 choose 1. This corresponds to 3 choose 0. This corresponds to 3 choose 3. Or you could have read it from right to left order, it'd be the same thing. Just as one more example, if I did 4 choose 2, I'd have 4 factorial over 4 minus 2 factorial, 2 factorial, which comes out to be 6, because each of these 2's cancels the 4, leaving me with just 3 factorial, which is 6. And that is this one right here. This is 4 choose 2, 4 choose 1, 4 choose 0, etc. So in general, if you wanted to know the ways of getting a certain number of heads after a certain number of coin tosses, you can use the combination coefficient if you don't feel like building out Pascal's triangle that far. So for example, if I was asked about 7 coin flips, I probably wouldn't build out Pascal's triangle. If I was asked about 4 coin flips, I would probably build it out because it doesn't take me very long. But maybe if you have 7 coin flips or 50 coin flips or 100 coin flips, I'm definitely not going to fill out the whole page with this little triangle right here. So let's look at a question here. So we're going to flip a coin. Let's say that we flip a coin 50 times, and we want to know what is the probability. Let's not say X. What is the probability that you get 25 heads out of 50 coin flips? Okay, so what we can do is use our combination coefficient. We have 50 coin flips, and we're choosing 25 of them to be heads. That's going to be the number that would be if we had extended our Pascal's triangle all the way down. That'd be the coefficient. And then what we're going to do is multiply that, or I guess I should say divide that by 50 coin flips, which is 2 raised to the 50th power. So when I did each of those probabilities, I did 2 raised to that power to get this. Like this right here is 2 to the 0. This is 2 to the 1, 2 squared. So as we extend all the way down, we'll get to 2 to the 50th power. So that's the probability that you'd get 25 heads. A slightly different way of writing that is equivalent is to say 50, choose 25, there's a half of a chance of getting a heads, and I need 25 of those. And there's a half of a chance of getting a tails, and I need 25 of those. And that 25 and 25 makes the 50 on the bottom. This idea right here on the left works because we had two outcomes with equal probabilities. This idea on the right is a little bit more generalized because the two different probabilities don't have to match. The one half here and the one half could be different things. So for example, and this will be the last example in this video, I'm going to take basically this formula and I'm going to talk about a biased coin. So let's say we have a biased coin where 3/4 of the time it lands on heads. Then the probability that you would have 25 heads would look like this. You still have 50 flips, and you're still choosing 25 of them to be heads, and I guess choosing the other 25 to be tails. But we now have a 3/4 chance of getting heads, 25 of those, and a 1/4 chance of getting heads, 25 of those. So let's compare these two probabilities just to give you an idea. So what's the probability with the fair coin? So green is fair, and then purple is unfair. And let's just see. I actually am kind of curious about what's the difference in these probabilities. So make sure you know how to type it in. So 50, choose 25, 3/4 to the 25, 1/4 to the 25. So I got this, 8.449 e negative 5. Then I'm going to go through and just change it to 1/2 and 1/2. And I get that right there. Okay. So you have about an 11% chance, if it's a fair coin, to get half heads. And you have an almost 0% chance if it's a biased coin, 3/4 and 1/4. Okay. So there you go. Let me know if you have any questions, and I'm happy to help out. Thanks.